All right, for your next field, we are going to start looking at magnetism. And here we have good old Magneto, our token representative for magnetism. If you don't know who Magneto is, that's actually a little bit sad, but I guess you have some X-Men and Marvel homework to do then. Anyway, we're going to start looking at magnetism. Now, magnetism actually has some very similar properties to electric fields that you guys have already taken. In fact, there's massive, huge connections between the two. Now, you can't really do too much with magnetism in grade 11. It's more about the ideas behind it and sort of how it works a little bit. And you'll take it in more detail and the mechanics behind it in grade 12. But still, the similarities and the connections between electric fields and magnetic fields for electromagnetism and a whole bunch of other stuff are absolutely massive. In grade 12, you take that in a lot more detail and see how the two can actually work together. So, but just based on the basic type stuff, they do have similar properties. For example, you have two poles, just like with electric fields and charges. Instead we don't have like positive and negative. We have, of course, the north and south. So you have north and south poles for a magnet. Okay, so for example, this is the token type of thing that you might be used to seeing, something like this. Here we got a picture of a bar magnet. There's north end, there's south end. And you can see the magnetic field probably made with iron filings going around it, something like this. And it looks almost identical to an electric field. In fact, if that was a positive and negative charge, the field would look almost perfectly identical. So even just the way the field appearance, the actual field appearance is often very similar. So how they actually look, just like electric fields, with magnetism, you can attract and you can repel, just like with electric fields. So these are all just a few of the similarities and connections between the two. Now, of course, if we would sort of draw a magnet here, let's draw a little magnet, maybe something like this. There we go, good. We have a north end, south end. Standard color coding for magnetic field is blue. And if we sort of drew a magnetic field around the magnet, something like this, sort of like what's in the picture, it is a vector quantity, and magnetic fields are drawn going from north to south. So they start at the north end, they wrap around and go to the south end, except actually inside, it'll keep on going towards the left, south to north, but outside the object, it goes from north to south. So when we draw the fields, the actual fields, and the symbol for magnetic field is actually a B, which may not make any sense to you, but if you want to argue that, you can go talk to James Maxwell, one of the smartest people who ever existed, about why it's a letter B. But anyway, the magnetic field, or the B, is actually drawn going from north to south. Okay, and that's the way we draw the magnetic field. Now, one of the things you may have done if you're a kid or something like that, and you had like magnets on the fridge or something like that, and you happened to drop a magnet, and the magnet ended up breaking. So you end up with like two parts to a magnet. So maybe I'll just redraw a little broken piece. There we go, something like this, north, south. One of the cool things about it, though, is you don't just end up with north end and a south end. Because if you've ever broken a magnet before, these two parts here want to stick back together, and in fact so do these. And it's kind of cool because here you'll create a new south pole and here you'll create a new north pole, and they will still attract to each other. So that's one of the cool things about magnets compared to electric fields, is when you have a magnet or a source of magnetism and you sort of split it up, well, you end up with smaller magnetic sections. So one of the questions that actually came up way back when is, how small can the actual magnets be? Okay, so how small can magnets actually be, and what's the smallest they can actually go? Like, can you keep on breaking these magnets up again and again and again and again? Like, how small can you actually make these things and still have magnets? Like, what's actually going on inside? And this led to some ideas and theories and discoveries of what's actually the ingredients, so to speak, inside of magnets. So what they found was, if you actually take a magnet is actually made up of little tiny magnetic sections inside. Okay, so it's not just one gigantic magnet, it's actually a whole bunch of little tiny sections. So we have these little tiny magnetic sections, and they're called domains, and this led to what's called domain theory for magnets. And it looks something like this. So this is the domain theory of magnets. So first of all, we're on color coding. They should be blue. Red is the standard for electric fields, but anyway. But it sort of shows these little magnetic sections inside a piece of iron or a magnet. And you can see when something is not magnetized, the arrows are going all over the place. But if something's magnetized, they're all generally going in one direction. So if I did the same thing on my picture here, if I would have these little magnetic fields, they don't have to be like perfectly parallel to each other, but you'd have these general little magnetic sections all sort of going in the same direction. The magnetic field then would come out this end, wrap around, and then go back this way, which is sort of the picture we had before. And this would be the north end, and that would be the south end of the magnet. So these little tiny domains are the magnetic sections, and I believe they're like on the order of like just under a millimeter or so, or a tenth of a millimeter is how big these little sections actually are. So you have these little tiny magnetic sections, and their polarity of their domains either cancel each other out, like in something that's not magnetized, or they sort of work together like something that is magnetized. And this also explains why when you break a magnet, you get smaller magnets. So if you break this magnet, well, you still have little north poles and south poles at the breaking point because the little magnetic sections are still there. So this is the idea behind domain theory, and how well those domains are aligned and what they can actually, how well they move, sort of dictate properties of the material. So if we look at those domains and how those domains work, so to speak, if they're random, then it's not a magnet because all the little polarities are sort of canceling out. If they are aligned, then it is a magnet, or it's magnetic. This also helps to classify materials, and there's different classifications of materials based on how the domains work. For example, you've probably heard of ferromagnetic materials before. Of course, the common one for that is iron, hence the Fe. And a nice way to think about it is they have ferromagnetic materials or iron have really, really loose domains, which means if you put them within a magnetic field, they will line up easily. And then you just have to lock them into position to make a magnet. But something that's ferromagnetic has very, very loose domains. It's a good way, nice way to think about it. So magnets work really, really well on ferromagnetic materials such as iron. Now there's also paramagnetic materials, for example, silicon. Anyway, paramagnetic materials have really, really tight domains. They don't shift and move very well. So materials then don't stick to a magnet. So even though they might move a tiny little bit, it's not enough for it to actually stick. So if you've ever tried to stick a magnet to metal or something like that, like aluminum or something like that, like it doesn't really work very well. It doesn't mean the domains aren't moving, but they're not moving nearly enough to actually have the polarity to actually stick. Now there's also something called diamagnetic, and diamagnetic also has really, really, really tight domains. The difference is both of these guys will attract, while this guy over here, this one will repel. So a diamagnetic fridge would absolutely suck because every time you tried to put something on your fridge with a magnet, the magnet would actually come away from the fridge instead of actually sticking the thing on. Okay, so this is how domain theory has sort of helped us figure out how materials actually work and how the alignment of the domains actually work in terms of the magnetic properties that materials that can actually sort of show us. So here's a picture of actual domains using a special type of magnetic camera, so to speak. Here we have like a zoomed in picture of a material, and you can actually see the little magnetic differences in the material, and those are the actual domains themselves. And you can see how it almost looks like a black and white picture taken from space, or like farmland or something like that, where there's different fields and stuff like that. But those are the actual domains within a material. and you can see how there's like differences in the magnetic polarities and that type of thing. Okay, so that's what it would actually kind of look like. Of course, you can't actually see this with a special, microscopes and stuff like that, but that's the way it is. Okay, so if we want to like make magnets and stuff like that, it's all about manipulating domains. So if we did want to actually make a magnet, of course they make magnets all the time. What they will typically do is they will typically melt the iron first of all. They put it into a liquid form. Now, first of all, so you can actually do two things with it. First of all, if you actually can do this, first of all, you can mold it, like you pour it into a mold, but it also helps to make the domains nice and loose because they can flow around. And then what they do is they can expose it to a very, very strong magnetic field. And of course, when you expose it to a strong magnetic field, this magnetic field actually then aligns the domains in liquid form. And then all you have to do is let it cool and solidify, and the domains can be locked in place, and you get a really, really strong magnet. And of course, the better the domains are lined up by the external magnetic field, the stronger the magnet's going to be. And of course, they can make some really, really, really strong, powerful little tiny neodymium magnets and stuff like that. Unfortunately, we're not in my lab. Otherwise, I could show you some of the cool ones I have in a lab. I've got one that I can actually use. I got a cannonball. You can actually hold up a cannonball with. There's lots of different cool things I could have shown you if we're in our lab, but we're not. But they can do some really cool things. You can just look up cool magnetic tricks and stuff like that, and there's lots of cool things that you can actually do with it. Now, this also happens naturally. The Earth, of course, has a magnetic field that goes around it. And if you don't know, the geographic north is actually magnetically south. That's why when you use a compass, the little red arrow, that's the North Pole on the little magnet that's inside the compass. Well, why would a North Pole for a compass be attracted to a North Pole? Well, it's not, because the North geographic pole is actually magnetically south, believe it or not. And what they found is the actual magnetic field of the Earth actually flips every few thousand years. So this picture right here represents the mid-Atlantic ridge. So underneath the ocean, of course, where the continents are coming apart. And if you actually go across there where the molten lava and magma is coming out, of course, the ocean, when the iron content comes out, it gets aligned by the Earth's magnetic field, and then it gets cooled by the water and locks into position. And they found that the actual magnetic field of the Earth actually switches every few thousand years. Now, of course, the Earth's magnetic field is all around the planet and stuff like that. And if you can go to places that have lava activity like Hawaii, this is a place where you can actually try to find naturally occurring magnetic deposits of iron, where the magma came out and the lava flows came out, especially when they're on the land and they had lots of time for the Earth's magnetic field to align the domains in the lava pools while they slowly solidify. This is where you get some nice, cool, naturally occurring magnetic type rocks. And if you go to Hawaii and try and go around using a compass in Hawaii, it can be kind of messed up because there's so many magnetic field fluctuations in Hawaii because of all the lava activity. I mean, they're just volcanoes. And there's other places around the Earth like that too, but it's really neat how the Earth's magnetic field actually can align the stuff if it's got time, enough time to actually cool and solidify and stuff like that. So, of course, the Earth's magnetic field is also really important for us because it protects us from the solar wind particles from the sun. This is basic grade 9 astronomy type stuff. So the Earth's magnetic field protects us from that. So if the Earth's magnetic field did get weaker, that would make things kind of tough. But it is kind of cool how sort of this type of thing actually works. So these are just the basics of how magnetism works. We've got these little magnetic sections called domains, which are the main thing for magnets. And of course, you get the North Pole and South Pole, and it sort of shows us why certain materials actually can be magnetized or not magnetized, or stick to magnets or don't, how well these little domains actually align, and why when we break a magnet, we can actually get smaller magnets out of it. But that's also why if you drop a magnet too many times, it doesn't work very well, because as it gets jarred when it hits, the domains get randomized, and then it doesn't work as well. Okay, so these are the basic fundamental ideas behind magnets and how it works.